In February 2016, the strongest storm ever recorded in the southern hemisphere battered the islands of Fiji. Cyclone Winston hit with sustained winds of 170 miles an hour, and by the time it passed, it had destroyed or damaged around 30,000 homes and impacted the lives of over 500,000 people. And in the village of Navala, sitting directly under the eye wall, stood about 130 houses built the traditional way, comprising thick grass roofs and frames lashed with rope braided from coconut husk. And when the wind finally died, more than half were still standing with little or no damage. But what makes these traditional homes unusual is that they defy the modern approach of using strong frames and heavy materials, which we consider an essential requirement for withstanding extreme weather. Not only that, but they cost 90% less per square foot compared to standard American construction. They regulate their temperature with no air conditioning, and they have been time-tested against fierce Pacific storms for centuries. So, how do they work? And what clever engineering allows them to withstand some of the most extreme weather on the planet? Let's find out. When you imagine storm damage, you probably picture the wind pushing a wall over until the house topples. And that happens, but it's rarely what destroys a building first. In most cases of extreme weather damage, the problem begins with the roof. When fast-moving air hits the flat face of a house, it piles up and changes direction, and that raises the pressure on the wall facing the storm. But the same air then rushes up and over the roofline, where it speeds up and pulls away from the surface, and fast-moving air leaves low pressure behind it. So you get high pressure pushing on the front of the house, and a zone of low pressure sitting on top of the roof, actively sucking it upward. It's the same effect that lifts an airplane wing. And it's worst at the corners, where the wind curls into tight spinning vortices that race along the roof edges. The suction inside those little tornadoes can peel, sheathing off like the lid on a tin of sardines. And once the roof goes, the walls lose their bracing, and the whole structure unzips. And what most people don't understand is that wind force climbs with the square of the wind speed. So if you double the wind speed, you don't double the force on the house, you quadruple it. A jump from 75 miles an hour to 150 makes the storm 4 times as strong against your walls and roof. A modern home tries to overcome this by attempting to be immovable, bolting the roof down while pouring concrete and steel to overpower the wind by brute strength. But the traditional Fijian house takes the complete opposite approach to this problem, and instead of resisting the pressure difference, it erases it. As we just learned, in a severe storm, a roof gets sucked upward because there's low pressure above it and ordinary indoor pressure trapped below. A solid roof of asphalt, sheet metal, or plywood seals the inside off from the outside, so the gap builds to its full, destructive size. A thatched roof is up to a foot thick, but it's woven from countless reeds with tiny gaps running through it. It's porous, like a thick sweater rather than a raincoat. So when the storm drops, the pressure on top of the roof, air is sucked up through the thatch from inside the house, and the pressure underneath drops to match. For the storm, there's nothing left to pull against, and the roof simply isn't being sucked anymore. Wind tunnel testing on porous roofs found that this cuts the peak upward suction by as much as 75% against a solid roof of the same shape. But eliminating the suction is only half of it. A storm still pours a tremendous amount of raw force into the frame, and the frame has to do something with that energy. A modern house tries to stand rigid and absorb the blow. And rigid things, when the load gets big enough, snap. A nail holds firm right up until the wood splits around it. The traditional house never tries to stand still. It's built to move, and is the second design secret of the Bures. Every piece of the Bure has a job. The roof is steeply pitched and hipped, sloped on all 4 sides rather than ending in flat gables. So the wind is guided up and over, instead of slamming into a flat wall. The walls are kept low, often under about 6 feet, which gives the storm very little to push against. The structural integrity of the building is supported by a massive central hardwood post, buried as deep as 10 feet into the ground. It takes the strain like the trunk of a tree. And the whole frame sits on a raised mound of packed earth faced with heavy river stones, a ballast that pins the house down and lifts it above the floodwater. But the real genius of these buildings is in the joints. The frame isn't nailed or bolted together at all. Every connection is lashed with magi-magi, a cord braided from coconut husk and wrapped around the timbers again and again. A bolted joint concentrates all the stress onto one rigid point, so when the wind shoves hard, that point either holds or shears off. A lashed joint spreads the load across dozens of wraps of fiber, and the fiber has give in it. The whole frame can lean and twist under a gust, soaking up the energy by deforming, then spring back to true once the gust passes. So, while the modern house meets the storm head-on and tries to win by brute force, the traditional house meets it by yielding, breathing through the roof, and flexing at the joints. And when you look at the real-world disaster data, it's clear this is an extremely effective strategy. Of the roughly 130 traditional Bures in Navala, about half rode out a Category 5 storm with no damage, or only minor damage. A handful collapsed, and a few more were badly hurt. But when a New Zealand research team went through the wreckage, they found that most of the damage to the Bures wasn't the wind tearing them apart. It was flying sheets of corrugated iron, peeled off the modern houses nearby, scything through the thatch like blades. And when the Bures did fail, they did so in a very different manner than their modern counterparts. You see, when a modern home fails, it tends to fail all at once. A roof-to-wall connection lets go, and heavy materials come down hard and fast. But when a Bure fails, it fails slowly. The light frame and soft thatch sagged and folded gradually, which gave the people inside time to get out. And even in the event of a full collapse, the springy poles left air pockets in the rubble instead of a crushing slab. When Fijian villagers of the 2016 cyclone were surveyed afterward, around 70% said they considered the Bures safer than the modern houses. And the laboratory studies backed the villagers' hypothesis up. Controlled tests at the James Cook University Cyclone Testing Station confirmed that porosity cuts those peak suction pressures by up to 75%. And full-scale work at Florida International University's Wall of Wind found that pressure-equalizing edges roughly doubled the wind speed a roof could take before failing. Which brings us to the real puzzle. If this design is 90% cheaper, this cool to live in, and this good in a storm, why can't you drive through a single American town and see one? And in reality, there are at least two reasons why traditional architecture like this will be nothing more than a novelty in the modern West. The first, and more prominent, is due to the fire risk. In the human environment of the Pacific Islands, where cyclones are the main natural threat, these houses are brilliant, but when wildfires are a primary concern, they start to look a lot less practical. A natural grass roof is dry organic fiber packed into thick, airy layers, which is close to the ideal recipe for a fast-moving fire. Under U.S. building codes, every roof on a lived-in home has to pass a standardized flame test and earn a fire rating, and untreated thatch can't pass it. You can coat it with fire retardant, but the cheap retardants wash out in heavy rain and have to be reapplied every couple of years. That's a real recurring cost and a real safety limit. But most likely, the single barrier to adoption is the difficulty in adhering to standard safety codes. To get a permit in the U.S., a licensed engineer has to sign off that the structure will survive defined wind loads. And to run that math, they need standardized strength numbers for the materials. Those numbers exist for milled lumber, steel, and concrete, because the industry tested them to exhaustion and wrote them into the codebook. They don't exist for a hand-harvested cypress log or a length of coconut husk rope, because every one of those is a little different. No standardized numbers means no engineer can legally stamp the plans, which means no permit. But there's one place in the country where you can build an authentic one, and it's a narrow cultural exemption. Under Florida law, a chickee built by a member of the Seminole or Miccosukee tribes is exempt from the building code entirely. And under a new state law taking effect in July 2026, that exemption is being expanded. Tribes are now protected from local bans, and the definition has widened to allow a wooden deck and even permitted electrical and plumbing. But the door stays shut to everyone else. That same law sets a penalty of up to $1,000, or a year in jail, for any non-tribe member who builds a chickee and claims the exemption. So you can't legally raise an authentic thatched hut in your backyard. But there's certainly lessons that modern buildings can learn from the traditional ways of the Bures. The first lever is pure geometry, and it costs nothing. The Bure survives partly because of its shape, and you can incorporate that shape on any house. Choose a hipped roof, sloped on all four sides, with a pitch of roughly 22 to 30 degrees. That's steep enough to send wind up and over, but not so steep that it becomes a sail. Keep your overhang short too, because a wide overhang is a scoop that the wind gets under and lifts. The second lever is the breathing roof, and the industry has already solved the fire problem for you. Synthetic thatch is molded from polymer to look like palm or reed. It keeps the porous, pressure-equalizing layering of the real thing, but it's rated to pass the fire tests and certified for winds up to 200 miles an hour. Products like these carry full Florida product approval, so you get a roof that breathes without the rot, the pests, or the open flame risk of natural grass. It isn't cheap next to asphalt shingle. But against the lifetime cost of natural thatch, which needs rethatching every few years and constant fire treatment, the synthetic version is dramatically cheaper to own. And if you want proof it works at scale, it's already standing in public. Disney's Polynesian Resort and a string of buildings across Florida use exactly this hybrid. A fully engineered, code-rated frame underneath, clad in fire-rated synthetic thatch on top. For most of modern history, we've answered the storm by pouring more concrete and riveting more bolts. And it's easy to assume that's simply what strength looks like. But a village of grass-roofed huts in Fiji has been quietly making the opposite case for centuries, and the engineers running it through wind tunnels now are mostly confirming what those builders already knew. Sometimes the surest way to beat the wind is to stop fighting it. If discovering underrated architecture is your thing, then be sure to watch our video on the monolithic dome home next.